Hello,
Thank you so much for
everyone. Hi, my name is Jacqueline. I work at HOK in the San Francisco office. So I guess just kind of apologize. We have to wear masks inside. So if you can't hear me at any point, please just shout out and I will also slow down because I tend to talk fast being originally from the East Coast. So yeah, I'll Devki, if you want to introduce yourself.
Yeah, hi, I'm Devki. I'm a structural engineer in the New York office.
All right. So we'll get going. We don't have, we realized that we didn't have a table of contents, so I'm just going to verbally tell you what we're going to be talking about today. Give you a little background what embodied carbon is, how we're involved at here specifically at HOK and our involvement, our approach to getting the analysis. We're going to show some case studies of typical buildings. Like Tony said, we generally do larger projects, not so much residential. So we'll show you kind of typical buildings that range from low embodied carbon to like a low operational net zero project or analysis that we did. How embodied carbon can be studied early during the project and throughout the project up to CA phase, and then close it out with the embodied carbon on a residential scale or like what you can look out for on a smaller scale. So also, I guess Tony's going to be monitoring the chat for any questions. I guess we'll just do that at the end, but happy also to do it as a discussion. If you just really have an urgent question that you can't wait till the end, we can by all means stop and answer that. So with that, just some background. So embodied carbon from buildings accounts for 11% of total global annual carbon emissions and includes the carbon emissions associated with material extraction, processing, manufacturing and construction, repair and demolition reuse. Most of these emissions occur before and after the use phase of a building when operational carbon that emitted during use of HVAC, lighting and appliances is greater. As engineers and performance designers at HOK, our goal is to reach a minimum of 50% reduction in both by 2030 and 100% reduction by 2050 at the latest to help prevent catastrophic climate change. So on the right here, we just have that pie graph, which showing, of the global embodied carbon emissions by sector, building materials is at 11%, and that operational is a total of 39%, but it does make up a big portion of it. And then here on the left, if we were to continue business as usual, by 2050, operational carbon is just going to keep going up and up.
Yeah, actually, another note about this graph, it kind of shows the time value of carbon for just one building. If we're looking to reduce 50% by 2030, like Jacqueline said, 74%, almost 2/3 of that building's carbon is all embodied. So it's just important for us to keep in mind when we're trying to reach these target dates that just a few years into the building service life, it's mostly the embodied carbon that's going to dominate it.
Thanks, Evie. And with that, I think I want to talk about the impacts.
Yeah, sure. So this is something that all of you might have seen before. These are the 6 impact categories that we evaluate our projects for per lead. But there's an infinite number of environmental impact categories. These were just chosen because they are probably the most critical. So whenever we do an LCA, whether it's in the building sector or other sectors, we'll use these 6 impact categories, and the units are provided here. So all of them are emissions except for primary energy. That is a measure of energy in megajoules. You'll also notice a little E next to the CO2 and some of these other emissions. That's because, for example, with global warming potential, there are many greenhouse gases, of which carbon dioxide is only one. So we multiply the other greenhouse gases by a factor to be able to consolidate it all under the kind of umbrella of carbon dioxide equivalents. For example, methane is 24 times more potent than carbon dioxide. We'd multiply the methane emissions by 24 and then add them to the carbon emissions. And then we just report one unit, which is kilograms of carbon dioxide equivalents. So that is a little background there. And on the right-hand side is just a little cartoon of a product life cycle. In this case, our product's a building. So looking at the timeline that I think everyone on this call would be really familiar with in buildings, from concept through design development, construction documents, CA, we're trying to reduce the embodied carbon, which is the upstream carbon emissions related to the structure and enclosure. We also sometimes look at interiors, and it's kind of everything, that all of the emissions that have already been emitted before the building is even occupied. So we are trying to reduce that starting at the concept phase. And we set some key checkpoints to see how we're doing. We can identify some setbacks. So we like to keep a little bit of a tracker as we're moving along in the project. And that percent reduction there compared to the baseline, that is something that's relevant when you are tallying up your lead points, because you get a certain number of points for a certain threshold of reduction. And again, just to bring it back to the intro slide, is we are trying to meet 50% by 2030 and 100% by 2050 at the absolute latest as an industry.
So that was a quick overview of embodied carbon, how we look at it through the projects. I just want to touch a little bit on what HOK's involvement with being part of two challenges, commitments. One of them, which you might be very familiar with, is AIA 2030. And so HOK is a signatory firm of that. The goal is, as an average, which requires continuous commitment review and reporting to ensure progress, that HOK continues to track toward a path that would get us to zero as a portfolio by 2030. So this is kind of our reporting going down. We are looking at energy code advancements and jurisdictional performance ordinances. And we report it through an AIA DDX. One thing that we are now shifting from energy modeling in renewables to more of a carbon focus. So there is now part in AIA 2030 where we have to report embodied carbon. And that's kind of where, next slide, the structural engineers come in. So HOK is also a signatory firm for another commitment called SE2050. This is brought upon as response to this SE2050 challenge, where all structural engineers shall understand, reduce, and ultimately eliminate embodied carbon on all their projects by 2050. So AIA came up with their 2030. Structural engineers were like, hey, we also need to do stuff as well. And so we came up with one, but have our timeline a little bit further out. We have an extra 20 years, I guess, to get down to zero, but it's supposed to work in tandem to get to that goal. So here at HOK, we are a signatory firm for both those. We've also just signed on to MEP 2040. We like our dates, apparently, in every industry. So yeah, being a multidisciplinary firm, we are trying to kind of stay ahead and really make a difference in tackling climate change. So with that, Davey's going to present a little bit on how we do the whole analysis.
Yeah, so there are many programs available to facilitate a life cycle analysis on a building. You can, of course, just do one in Excel. All you really need is your emissions factors for your materials. However, when we are working on a building project, beyond just the structure, maybe we only have a few materials through the structure with steel and concrete and timber. But then once you start getting into enclosure and finishes, then the number of materials you're trying to manage in your spreadsheet snowballs a bit. And so these programs all serve to help you interface with all of the databases worldwide where these emissions factors are stored. So there are a lot of national databases in the US. There are plenty of databases abroad too. A lot of these programs draw from both local, national, and international databases. And it gets quite as local as you can get an EPD, which is an environmental product declaration. It's kind of a nutrition facts label for any material that you're using on your project, except it'll have emissions factors on it. You can get that from your local concrete supplier or window supplier, and you can input that data into these programs too. So it's really just data management and interfacing with these databases. And a lot of the databases you do actually have to pay for access to, but with these programs, you don't have to pay for the access. The program kind of takes care of that. So it really makes our lives a lot easier when we're doing LCAs. We only have to go to one place. Some of these are free. I think that's important to note. EC3, Athena, the SOMEA tool. I'm not sure about OneClick and Tally. OneClick is quite affordable for a firm, even a small firm. I'm sure it's free. It's free for students, but they all suit a different point in the in the timeline of the project. We rely really heavily on OneClick LCA. I think a lot of us have tried all of these, and the OneClick LCA is really doing the best job. Something to know about EC3 is you can just log in and start using it, but it doesn't look at the entire product lifecycle. It just looks at everything from cradle to gate, which is materials extraction to manufacture, to the point at which it kind of arrives on site. And then everything beyond that point, which is relates to maintenance and disposal, end of life, recycling, that's not really included in EC3. So it's important to note that that is not a full life cycle analysis, but it can certainly help you choose between products. So moving on from here, the next slide shows our workflow with OneClick LCA. We usually start with a BIM model, but you don't have to have a BIM model, especially if you're in the early phases of your design process. Even if you tabulate your bill of materials in Excel, that works. If you have a BIM model, you can export your bill of materials from there. And then we just go ahead and upload it through the OneClick interface, do some post-processing because things aren't always modeled perfectly in BIM programs. And then you get your first iteration of emissions results. And you might notice here that these circled emissions results, this is a percentage. So this represents the change from a baseline. And that indicates that you have to do a life cycle analysis more than once to see what your improvement is. You need some sort of baseline beyond which you're improving. Yep. So here is a look at some results. So we're just jumping right into what the results look like. You can get a breakdown of your carbon, for example. You can also do this for any of your other emissions, but we're focusing on carbon. Okay, where does baseline data come from? That is a really good question. I'll just stop to answer that right now. That's something that's actually giving the industry a lot of grief because there's no clear, there isn't always a clear baseline for a given typology, a given functional unit, which might be the number of patient beds in a hospital or the number of bedrooms in a residential multifamily building. There might not always be a clear industry standard. So the baseline is in theory supposed to be the industry standard building for a given typology in a given region. Sometimes that's really obvious. For example, if we're designing an office building and we're putting it in a corporate park where all of the other buildings are tilt-up concrete, that's very clearly the baseline. So we would do some quick calculations to see what the bill of materials would be if we had designed the baseline building, and we compare it to what we actually did, which might be composite steel with curtain wall or some sort of masonry facade. Sometimes especially the projects we work on, a lot of times they're really specific, and in those cases, there isn't a clear comparison because the requirements for the project were really, really specific. Sometimes we have university guidelines that dictate how the outside of the building has to look. Sometimes a certain structural material is requested because the client is comfortable using it. They've done it before on their other projects. So what we do in those cases is we compare the building to itself at concept or schematic, and we track how much we've improved from our starting point that met all of the requirements of the project. And yeah, that is what we've done here. So this is a university S&T facility. It's cast in place concrete. we track the reduction in the overall concrete from where we started on this project. And so first we pinpointed the carbon by life cycle stage. As you can see here, most of it is in the materials extraction, processing phases. And then we also see this breakdown of carbon amongst the different material types. You can see, because we designed a concrete structure, most of it's concrete. You'll see on another slide that even if you design a steel structure, sometimes concrete is still the largest piece of the pie because of the foundation. And then we have some polymers, glass, etc. So what I want to actually draw your attention to on this slide is this pie chart in the right. The roof construction, exterior walls and exterior windows, that all comprises the facade of the building, and everything else is the structure. So you can see that the carbon for this project is split 50-50 between structure and enclosure. And I think that's not what anyone would really guess going into a project. I think one would think the lion's share would be in the structure, and then maybe the facade would be 25%, but it's really 50-50. And this is the type of facade here is curtain wall that is non-negligible in terms of the amount of carbon. Then also you see a lot of the stone cladding, and that stone cladding is hanging on CMU. And that CMU is non-structural, so it's really just a dead weight on our structure. So there's a lot in that facade. So moving on to the next one.
So this is another case study, which was a composite steel laboratory building. Very similar graphs, just different colors here, but we first looked at it by life cycle stages. You can see again, materials is going to take up most of it. And now, even though it was a composite steel building, you can see by this middle graph here, the concrete actually probably just over 50% more, just over a majority being the largest contributor to CO2. And we can see that when you break it down even further by the building system here, we see that comes mostly from the substructure, the foundation, which is concrete. And so even though it's a steel building, the foundations is a big portion of it. And then actually, unlike the university project that JP just talked about, our glazing and curtain wall was not split 50-50. This building, it's like 900,000 square feet, and just the, I think, sheer volume of the envelope as compared to substructure and everything else, superstructure, is just not as great. So we were expecting to see a little bit more, but this is kind of what we've come up with when we ran the whole building analysis. This is another case study that we have done. It's a government building. So all those other buildings were new builds from the ground up. This is a low-embodied carbon building is what we're calling it. And it's actually looking at it as a retrofit. So here's just an image of the building. It's a government building, as I said. And they wanted to look at what the savings was from retrofitting. And so we did a comparison of all the new stuff that was going into the retrofit renovated building as compared to as if they were just going to build a whole brand new building. So what this graph is showing here on the left is the yellow orange line, that straight one down below is just the total embodied carbon, and that's going to remain the same throughout the life cycle, the life of the project. And then the operational carbon is what that blue and orange line are. And if it was just to operate as normal, it's that orange line that's just going to keep going up and up. But we looked at the embodied carbon and operational, and they were able to propose a operational carbon that is that blue solid line. And then as we compare that to a new replacement building, is what we've called it, is those dashed lines. You can see that the embodied carbon of a new building is that dashed blue line. It's a lot more. It starts out at 11 million kilograms of CO2 equivalency. And then if they were to use that same proposed operational use of their systems, HVAC systems, you'd get that dashed green line. So together, the operational embodied carbon make up the total carbon emissions of the building. So as this was, you kind of always hear renovating or reusing a building is better than building new. And this is actually like numbers put to that statement. So this is just another graph, another way of looking at it. We stacked up by the building elements, looking at on the left, you can see where the foundations, beams, columns, slabs, etc., up through the facade. There's a 6.4 million kilograms of CO2 equivalency avoided by renovating the building as opposed to building new. And then just kind of, again, looking at it visually, what does that really mean to scale? And that 6.4 million is about 7,635 acres of US forest to sequester the same amount of carbon in 1 year's time. That 7,635 acres is equivalent to about 5,784 football fields of forest. So not a small amount. And just again, looking a little bit more at this picture of the building, it was kind of hodgepodge, started in 1905 as a U shape, and they added some more, and then they added some more, and that's where that like kind of, we call it figure eight building, and they wanted to preserve all that for the most part, and then some structural retrofit was done. They essentially, the walls were not great and shotcreted all the walls, and even with shotcreting all of the walls, it was still significantly less than building new. When we compare that to the interiors, so typically we don't look at interiors, especially for LEED. It's now coming more into the market in terms of analyzing interior products. For this particular study, we did look at interior renovations because they essentially gutted out the building and put in all new finishes. So we really also wanted to look at what those interior finishes, how that stacks up to the actual structure. Small portion in relative, it's only about 25%, it's about a quarter of what the structure is made out of. So when you're looking at where you can save, you want to start with the structure. You can definitely find some savings in interiors, but it's not going to be as significant. So that is the retrofit interior finishes project. And Daisy's going to talk about another one that we've done.
Sure. And we had a very pertinent question come in just this moment. What project phase, let's see if I can pull that back up. What project phase do you typically start analyzing embodied carbon? We try to start analyzing it as early as possible. And I think this is a timely question because what we're just about to look at is a concept phase LCA, and we have some results that come a little bit later in the deck of a CA phase LCA. So while the process is conceptually the same, we're looking at different things. So early concept, we are comparing different structural systems. Do we want to use concrete, steel, timber, etc.? And we'll be trying to set the course in that sense. But then if you fast forward to CA, it's more geared to which concrete submittal, which concrete supplier or mix design do we want to use? And then we're going to compare the emissions from different concrete mix designs. So more on that shortly. So this was a conceptual study. We can go to the next slide of how to reach net zero in a laboratory facility. And this was geared towards new construction. So because we actually do a lot of new construction laboratory facilities, of course, retrofit is always going to be better environmentally, but this looks at 3 new construction options. We have our base scheme, which is reinforced concrete. We had one scheme which was proposed as possibly better, which was steel and then precast deck. And then a third scheme, which we were anticipating would come out ahead, was the mass timber option with, it still had some concrete columns, though we couldn't do concrete columns all the way down due to the lack of, we can do mass timber columns due to limited strength. So what you can see here is our hybrid medium option came out to be the worst one, but the take-home message is the mass timber was in fact significantly ahead of the steel and concrete in terms of the carbon. I think something that is notable here, though, is that the foundation, which is orange, that's the biggest piece of the pie in all 3 cases. So that's really, really big kind of low-hanging fruit, is if you can find some way to reduce the quantities of the material you're using on the foundation. Maybe there's some existing foundation elements in the field that you can make use of. Maybe you can put as much fly ash in the foundation concrete as possible to reduce your reliance on cement. All of those things will reduce your carbon emissions associated with the foundation, because again, what we can't see, it's underground, it's actually the biggest piece of the pie. And below the gray line, yes, thanks for mentioning. That's a good segue into what is this negative carbon here. So in the timber case, we did account for biogenic carbon sequestration, which is the carbon absorbed by that building, or by that, sorry, that tree in its life cycle before it was harvested for construction. The reason I separated this out and present it as a separate negative value is because you can't always claim that for your own carbon reductions when you're tallying up your emissions related to a timber building, whether it's light frame timber, whether it's mass timber. The reason pretty much lies in how it was forested, how the forest was managed. If it's FSC certified, typically you can claim that carbon sequestration in your building design. If it wasn't FSC certified, definitely not. It's kind of a hotly debated issue. And part of the reason is that having a certain part of the Earth's surface be forest is essential to global level carbon balances. So if we're counting some of that sequestration towards lowering our theoretical building carbon footprint, are we maybe double counting? So I've presented it here separately, but I guess what I'll leave you with is the wood has to be FSC certified at a bare minimum. So we'll go to the next slide. So I'm not going to go into this one in great detail, but it just shows how our sustainability team went through many iterations of energy modeling and whittled away at the operational energy use of this facility as well in the concept phase. And you can see the steps were air tightness, air change, insulation, glazing performance, shading, and glazing ratio. It was done kind of sequentially. That being said, there is a certain amount that could not be covered. So it would still require a 25% offset to get to net zero. We looked at different types of facade options. This is from one of the sustainability group's architects. And the base option, we have some precast concrete panels, and that seems to be quite common in a lot of new projects, though I think we're all pretty familiar with the fact that it's not going to be the best in terms of carbon. But then we look at hybrid steel. So this is kind of, can we move in the direction of more environmentally friendly materials, but then still retain some of the benefits of aluminum cladding? And the result was this actually was the worst case as well in the facade. So I think the take-home message is, either just go the whole way, go green, don't go halfway. So the mass timber, we looked at timber cladding as well. That one came out well ahead of the other two. When you're proposing this on projects, sometimes it can be hard on the large projects to sell timber mullions, but we are going to have to make some pretty dramatic changes to see dramatic results. If you're doing smaller multifamily buildings, residential architecture, it's a lot easier to get timber frame windows. And this shows that there's a good reason to. This is just a visual comparison of the carbon footprint, or I try not to use the term carbon footprint, the total carbon of each scheme.
So we looked at a study in the schematic design really early of an office building in San Francisco, just seeing how the material changes against similar, I guess, kind of what Dave Key presented on her net zero project, but this was just for an office building. It was baseline was, I believe, cement replacement, and then just how much you can save throughout going up to mass timber. So this was just something that we could do at schematic design quite early. You can just kind of see material choices and how that changes your embodied carbon. So, and then also along the lines of, starting early, that question, we looked at bay studies for by vibration criteria and different sizes of bays and different materials. So this is just looking at all 6 impact categories. We usually focus on that global warming potential, but you do want to look at all of them, especially when it comes to LEED, seeing how even though maybe hybrid, that, green, this gray is quite low, it does jump up in terms of maybe non-renewable energy and biocarbon sequestration here. So.
Yeah, the biogenic carbon storage is actually that's a good indicator.
Yeah.
But like Jacqueline said, LEED does prevent you from getting any points for reduction in global warming potential if you have increases in more than 5% in any of your other categories. So you can see that that's actually a real challenge sometimes.
And as I mentioned earlier, we don't typically look at interiors. However, we have looked at them specifically for this one project. The client really wanted to, it's only an interior renovation, and wanting to look at different material choices. So we found that for interiors, the top 5 finishes for the worst performing is the chipboard. So that is the partitions, and carpet is a big one. So those were kind of like foundation, where that's going to be a big portion of your overall embodied carbon. You really want to tackle the top finishes that are the worst performing. So that would be the gyp and carpet. And yeah, just looking at what interiors finishes, how that shakes out.
This is something that I mentioned earlier about CA phase LCA. We're looking at something completely different at this phase. We're not able to make really large changes like massing or structural material or the facade sort of assembly, but we can choose between different suppliers of the same product or different concrete mix designs. And your concrete mix design is so crucial to the overall sustainability of your project. So this just shows going from, for example, 0 fly ash in the superstructure and 40% fly ash replacement in the foundation to 30% in the superstructure. That alone can get us almost a 10% reduction in global warming potential of the whole project. And this was a very large project. It was a large S&T, a lab facility for a university. So that's a really big number when you consider the total carbon expenditure of the entire project. And just for a little bit of background, when we talk about fly ash percentages, that value is the amount of fly ash or slag or any other cement reducing material or pozzolanic material. You might have heard it called a pozzolanic material. So it's the quantity of, say, fly ash divided by the quantity of cement plus the quantity of fly ash. So it's the cement replacement divided by the total cementitious material. And I know I might be kind of waxing poetic about concrete right now, but that's because it is incredibly crucial to the sustainability of your project. It really comes down to the mix design. And given what we saw with the net zero lab results, how large a piece of the total carbon puzzle foundation is, it can be a little bit out of sight, out of mind, but a lot of your carbon emissions are in that concrete foundation that's underground. So if we go to the next slide. Okay, so we changed pace here for you guys because we know how much you think about insulation with Passive House. So enough talking about concrete. Jacqueline, do you want to introduce the little study we did here?
Yeah. So yeah, as JP said, we knew that you guys are probably more interested in insulation. So we took a look at different insulation types and found what the carbon intensity was to get an equivalence of an R value of 60, and then ranked them here. So yeah, that's what is showing here.
Yeah, so you can see cellulose is doing great, spray foam not so much. And we got this closed cell. Yes, that's closed cell. I'm not sure what HFC stands for. Again, I plead structural engineer, I'm sorry. But yeah, so the foams are typically the worst performers, and that's kind of been found across the industry. A couple of years ago at the Carbon Positive Conference, which is all about buildings going for low embodied and operational carbon. A resounding message in a lot of the presentations was you can't get to the carbon reduction we need to get to and use rigid foam insulation. So that's kind of the first thing that has to go. And it's a little tough because it's such a high performing product in terms of energy efficiency. But then when you look at the embodied emissions that are upstream in order to create that product, suddenly on the embodied side, you're paying a really heavy price for it. So you can just take this at face value. If you have any insights to share, insulation, we would be really interested to hear them. So at this point, we can just turn this over to question and discussions.
Thank you. Well done. So if you guys have questions, maybe just type into the chat and we can queue you up. Awesome data. I have a question about the, if I may be so bold to go first. In terms of the structural engineers piece of jumping into the embodied carbon modeling, you know, one of the things that is of value on the AIA 2030 modeling is the idea that we're generating a database ultimately to help understand and dissect and, you know, slice and dice the carbon in many different ways. So it helps us basically benchmark where we're at, figure out how to improve. And it seems like that is also the intent of the structural, the SE2050 is to generate this database and start to get a sense for what the biggest drivers of carbon are and how to improve and basically create a shorthand for how to get there faster, right? Can you talk a little bit about either that effort or kind of what you've learned through sort of modeling numerous projects and trends? And I know you already talked about concrete quite a bit, but anything else that you want to draw out of that?
Yeah, I'll go first. I've been heavily involved in the SE2050 information. So that started, I think SE2050 started around like, what are we, 2022, 2018 or so. So still fairly new. And I will, not to necessarily toot our own horn, but HOK is kind of leading in terms, or we're definitely one of the big players in looking at embodied carbon. And we kind of always knew, I think, that concrete was a big player. The steel industry is getting more on board doing like recycled concrete, recycled steel. Wood is becoming more prevalent. I'll repeat what you said, like AIA2030 is they have a decent database right now. We're still kind of in the data collection phase, to be completely honest. Companies who are signatory firms have uploaded their information, and just right now they're kind of plotting it all out to see where typical projects land and then like really how to reduce it from there. So yeah, I don't know if I answered your question really. If Dave Key had any more to add.
No, nothing from my end. Does anyone else want to join the discussion? I know that there are several questions that came through, but you can feel free to unmute and just.
And sorry if I missed it. The SE2050, is that a commitment to model what? All of your projects?
So SE2050 just requires substructure and superstructure and just reporting a global warming potential number. So you don't have to go into any kind of like reductions or anything. And it's just at any point in the project. So pretty bare bones, I guess you could say. And then I guess at HOK, we have our own policy to really kind of move the needle, is to run LCA on all our projects. That way you can really get a full portfolio of different types of projects. The commitment actually really only requires 2 projects to be uploaded every year with no more than 5. And so I think they didn't want to scare signatory firms into like doing so much more work, but the more information that we can give them, the more it's just going to help the whole industry. So yeah, just structure. We don't need to include enclosure. For LEED, you do need to include enclosure.
And you guys talked about carbon quite a bit too. I know for University of Michigan, we were contemplating trying to use carbon cure. How does that stack up against fly ash?
Yeah, that's a great question, Tony. It's about a 5 to 10% reduction. So it's equivalent to using a 10% fly ash mix.
Good. And then looking in the chat here, not to totally take over the conversation, sorry. So Tom posted, check out Builders for Climate Action, recent publication for smaller scale buildings. That is a pretty awesome report. And they also have a modeling tool as well for residential projects. They boast that it can do up to kind of mid-sized mixed use. It is, from what I can gather, also a glorified spreadsheet, but user-friendly and geared towards builders to be able to do that as well. Let's see, I think there was one other question in there. Textile waste for concrete or brick production. Karen, if you want to unmute yourself and chime in.
Yeah, thank you very much. Actually, I was studying at IIT a few years ago and just accidentally started focusing my research on textile waste. And when I started realizing how massive of a problem that is, I challenged myself to think about ways to reuse textile waste for products that had longer life cycles. So staying out of the apparel industry altogether, because it really bothers me to think about that. I started thinking about using it as, for brick composition or siding or roofing materials or anything like that. So I keep hitting these brick walls, no pun. And it's because the textile waste is so inconsistent. And like, for example, if you use it for brick, it would just disintegrate the brick because it's all plastic basically. So I was wondering, other than things like insulation and soundproofing, are you seeing any trends for using textile waste in any other capacity for construction materials?
I think I haven't personally looked into textile use as it relates to concrete, but when we do get the emissions factors for any given material, it is supposed to at least account for the emissions that went into creating whatever textiles that they needed to use if they needed them in their process.
I'm just talking about like structurally, have you seen anything where textile waste can be, other than like the most common uses now are like stuffing in furniture or airplane seats or train seats, dog beds.
Yeah,
I would just like to get into something that is a significantly longer life cycle than those types of products.
Sure. I have only 2 thoughts and then I'll see what Jacqueline's are. One is obviously cellulose insulation. They use a lot of recycled denim and we looked at our chart and the cellulose came out ahead in terms of having the least global warming potential for an R60 value. So recycled denim is a really good example of that. And then I know that a lot of interiors finishes do use recycled textiles, and it looks like Ted has shared that information as well. What do you think, Jacqueline?
Yeah, I think in terms of structurally, unfortunately, it just wouldn't give us the performance that we would need out of textiles. It would be interesting to see if they, I mean, this is a complete shot in the dark, but like whether it could be used in some sort of cement replacement, but I just don't think it's there structurally for performance that's feasible. So.
We are at the 6 o'clock hour. We should probably wrap it up. Maybe take one last question, if that's all right. From Will Erickson, how are you to integrate into the design teams? What intervals of projects do you model the embodied carbon, or is it more of a continuous process?
I can start answering that question, then I'll hand it over to Jacqueline. So when we are doing our own projects, when we're the structural engineer on the project, it's really easy because we have a constantly running bill of materials for our own design. And we can run it through OneClick LCA or apply our emissions factors whenever we change something. And I did that for the project that I worked on with Tony, which was the university hospital. So that kind of generated a live carbon tracker for the client. And then Jacqueline can share how we help design teams when we're not the structural engineer on them.
Yeah, so when we're not the structural engineers, sometimes we get in early if we're on like the good side of the architects. Otherwise, we do just try to emphasize like the importance of running an LCA. And so we work with the structural engineer of record to get the bill of materials and then run the LCA on our end and then report back if there's enough, I guess, kind of, money in the project to run further iterations, then we will and provide some recommendations. I just wanted to touch, actually going back to another question before we finish up, that Francis asked, and it's not a basic question, but why structural engineers are involved in the carbon reduction. You might think that like, why isn't it coming from the architects or anything? But I think, as we saw, the structure is a huge portion of the embodied carbon, and we don't want architects to be kind of telling us what structure they should be using, because honestly, we're the experts on what's going to, I think, work best for their design. So we kind of really want to keep it in the structural engineer's court to find what's optimal for the safety and well-being of the building. So to answer that question.
Excellent way to wrap. I didn't mean to skip over that one. Thank you for circling back. And of course, we need everybody to be involved in solving this enormous challenge that we have in front of us. So very excited to have the structural engineers using their great skills in a way that makes sense. And so thank you guys for all the good work you're doing.